Hi everyone, it's Mrs. Sommer here to talk about Lesson 401, Collision Theory and Activation Energy. In this lesson, students will be able to describe collision theory, explain the three requirements for a reaction to occur, define activation energy, and interpret graphs representing energy changes during chemical reactions. If you remember, a chemical reaction is a process in which atoms of one or more substances rearrange to form new substances. So bonds break and bonds form. So I want you to think about this question. If you were like Ant-Man and could shrink down to the size of atoms in the middle of a chemical reaction, what do you think you would see? Complete chaos would be the answer. You'd see complete chaos. Collision theory states that in order for a reaction to occur, particles must collide. They must collide with enough energy, and they must collide with the correct orientation or the correct angle. So if you look at this reaction, they're not going in at they're wrong orientation. They're not positioned right to collide and react. In these ones, they don't have enough energy. They're not meeting each other. Well, here, they're in the right orientation, and they have enough energy to collide. So think about kissing. So if you kiss somebody, you have to have the right orientation of your faces and enough energy, because otherwise you're going to bump noses if you go in too fast, or if you're like middle school, you're not going to get close enough. And so it's just like collision theory is just like kissing. So not in this picture, not orientation, and clearly there is not enough energy to make that happen. We will be watching this video live during our session on Tuesday morning, Tuesday afternoon during our class live session. I will be showing you this video. Activation energy is the minimum energy required for a reaction to start. So think about, it's like pushing a ball up the hill. So you have to have a certain amount of energy to get to the top for then it to come back down and show the reaction. Every reaction has an activation energy. Some of it is some reactions that spontaneously occur have a low enough reaction or activation energy that they don't need any extra energy to be put in for the reaction to happen. Others have such a high activation energy that they need something to help it start. So think about this question. Which hill would take more energy to get up? So if you guessed B, you'd be correct. B, it would take more energy, and in that regard, it would take more time for you to push that ball up the hill, because it's a steeper hill and it takes more energy to push that ball up the hill. Whereas in A, it's a tiny hill, it still takes energy, but it doesn't take as much as compared to hill B. In your notebooks, I want you to draw this graph here. I know it doesn't have anything on it right now. And then off to the side, draw energy, reaction progress, reactants, products, and activation energy. In the next slide, we will be showing you where all of those fit in on your energy graph. So if we were to represent a reaction on a graph, our energy would be on the y-axis. So our y-axis is our energy, and our reaction progress is the x-axis. So reaction progress, or the time it takes, is the x. Energy needed is your y. And so if we're starting it, we have our reaction, our reactants over here. And then we have this graph that looks like this. And in here is our EA. EA is activation energy. Now, in our next lesson, we will talk about the endo and exothermics, and their graphs look a little bit different, but they each have the same reactants, activation energy, and products, but where they are in terms of the amount of energy they have is different. So in your notebooks, you should have copied this whole graph down in order to better understand what a reaction graph looks like. So here's a question: which reaction requires more activation energy? So more energy to get started, graph A or graph B? If you guessed graph B, you would be correct, because if you look, the amount of energy required to go from the reactants to get it to react, to come back down to the products, is a lot higher than the activation energy required in graph A.